Okay, it's great to be back. So 3 years ago, I gave this talk about dark halo response in the magic simulations, and I was in Heidelberg. Now we have an upgrade to magic called NiHao. I've moved to New York University in Abu Dhabi with Andrea Macchio. Liang Wang was the graduate student who ran all these simulations, so a lot of credit has to go with him. And Avishai has been helping out with the toy model. Okay, yeah, so this is just a movie of one of the simulations. It's a dwarf galaxy. This is a big scale, and this is sort of a little bit bigger than the Vera radius, and it's a gas temperature map. And so what I just want you to notice is just the outflows. You see this violent process. Yeah, a lot of outflows. And you also, you have outflows, you also have inflows. Okay, so I guess your questions are, where is Abu Dhabi, and what's the weather like? So I'll start with that. I'll give a brief overview of NiHao, although I won't have to say too much because we've already heard about this. And what are the new things we learned about dark halo response from NiHao? Okay, so Abu Dhabi is the capital of the United Arab Emirates. So it's over here in the Arabian Peninsula. It's near Dubai. You may have heard about Dubai because it has the world's tallest building. It's so big you can write the size in kilometers. And it's not too far. It's about an hour and a half. And often, if you fly to Asia or Australia, you can fly through Dubai or Abu Dhabi. No, it's not that. But it really does stick out relative to all the other buildings around it. So NYU is over here. This is sort of the main downtown area. Yeah, the weather, it's usually quite sunny, but sometimes it's cloudy. So it feels like here. Back to the science. So this is the NiHao galaxy simulations. We ran 91 zoom-in simulations using gasoline SPH. This is using the upgraded gasoline, so we largely fixed the blob problem. It's lambda CDM in the Planck cosmology. There's standard things, UV background, metal-dependent gas cooling, star formation with a threshold of about 10 atoms per centimeter cubed. Chemical enrichment, and we have two types of thermal feedback. We have the supernova feedback, and we have thermal feedback from the stars before supernova go off. So this is just the same thing you've seen before. It's a halo mass, a dwarf halo of about 10 to the 10. Okay, so one of the nice things about NiHao is that we sample 3 orders in halo mass, and we're consistent with the stellar mass halo mass relation, not only at redshift 0, but also redshift 1, 2, and 4. And this is purely because of the stellar feedback we put in. If we just use the supernova feedback, you overcool a high redshift. So if this looks too good to be true, then yes, partly it is because it was calibrated in a Milky Way mass, and the early stellar feedback was chosen to match the evolution. But all of these things here just come out. We haven't tuned any of the dwarf galaxies. Okay, so another thing we have is we have a uniform mass resolution. So this is the number of dark matter particles per halo as a function of the halo mass. And so if you have a fixed volume, then your tracks will look like this. And so you have very good relative resolution in the massive halos, but your dwarfs are not so good. So one thing is you could do many different volumes. That's sort of quite expensive. We wanted to get a sample, a reasonable number of objects. But without spending a lot of time in doing volume. So the key thing we wanted to resolve, so this is the convergence of at least 1% of the Vera radius at redshift 0. And this number is important because the sizes, the half-light radii of galaxies, are typically 1 to 2% of the Vera radius. Andre has a nice paper that shows this. So we want to dynamically resolve 1% of the Vera radius in a dwarf as well as in a Milky Way. And so that's why we have this step system. And the thing you'll notice, though, is that the feedback model is able to work with different mass resolutions. Right? So the physical resolution here is much better than here, but we're still able to get reasonable stellar masses. Okay, so one of the goals of the way we set up the NiHao simulations is we want to make a prediction for the structure of dark matter halos, and in particular cold dark matter halos. There's 2 reasons. One is so you can constrain the nature of dark matter using observations of the dark matter density profiles and the velocity function. And also something that I've been interested in a long time is the origin of galaxy scaling relations, in particular the scaling relations that link the luminosities or masses of galaxies with the dynamics, so the Tiley-Fisher, Faber-Jackson fundamental plane, and understanding these requires you to understand how the baryons and dark matter interact. So 3 years ago I showed you this plot which shows you the inner slope of the dark matter halo measured between 1 and 2% of the virial radius versus the ratio between the mass in stars and the halo mass. And so you have this U shape. Over here, basically nothing happens because there's very little star formation. As you increase the star formation efficiency, you get more expansion, you get a core, and as you end up forming more stars, the expansion is not sufficient. And then when you're over here, you get contraction, and these are simulations of overcooled, and you get a lot of contraction. And so this is the result from the Niehaus simulations. The dashed line is the fitting formula from MAGIC. So really not much has changed. We've just been able to quantify the scatter a little bit. The red is the hydro, and the open circles are now the matching dark matter only simulations. So you can see there's in the low star formation efficiency, nothing really changes. When you're in this efficiency this ratio between 1% or less than that, then you have a lot of expansion. This is sort of roughly where the Milky Way is. The ratio is about 5%, and so roughly there's no change, although it depends on the details. Okay, so one of the nice things about this is it's dimensionless, but the problem is alpha is it's a derivative of the density, which is the derivative of the mass. So you're looking at a double derivative of the mass profile, and so this is noisy in the simulations as well as the observations. And so I decided to look at the mass profiles. I like to plot circular velocity because it just compresses the y-axis a bit. So the circular velocity is just the measurement of the enclosed mass. This is from the dark matter only simulations on the left, and so the green line is an ASTO profile with a 2 sigma scatter, so it recovers what we expect for dissipation of simulations. And on the right, we have the hydro simulations. So there's a lot more larger diversity here. You can see here these are cores. These ones over here, these are the MUG simulations which I included, which have overcooled a bit, and they've had quite a strong contraction. So to show this in a bit more detail, I'm just looking at the ratio between these two curves at 1% of the virial radius. So this is basically the smallest scale we can reliably resolve. And so you'll notice a few things. So the lines are all color-coded by the star formation efficiency. I've now divided by the cosmic baryon fraction. So this number goes between 0 and 1. You can see there with the color code. So if your large radii, so greater than 10% of the virial radius, there's not a whole lot of change, which may not be surprising. And as you go to smaller radii, then everything just blows up. Right, so these circles are actually the half mass radius. So there's a hint there that there's a dependence on the half mass size. Again, we see that the maximum expansion is occurring with efficiency between 1 and 5%. And when you have a very efficient galaxy formation, star formation, you end up with contraction. So we found that the best parameter was the star formation efficiency that correlates with now I'm plotting the change in the mass. So this is just the velocity ratio squared. 1 means there's no change. If you're above 1, the halo is contracting. If you're below 1, the halo is expanded. But then the other parameter we found, these are now color-coded by the size of the galaxy. So this is the half mass radius of the stars in units of the virial radius. And so if you're over here, these ones are bigger than these ones. And this actually looks even better if you just plot the halo response mass ratio versus the epsilon r. And then if you just ignore these galaxies, which are the low mass ones, very low efficiency, then there's a nice power law. And so then we can use this just to make an empirical fitting formula which links the change in the dark matter profile versus two parameters, the star formation efficiency and the compactness of the galaxy. So the black lines are the simulation and the shaded region, and then the dash is just the analytic fitting formula. So this is something you can use if you do mass models of galaxies. One of the correlations we just saw was if you have the stars expand with the dark matter. So this is a bursty star formation history. The green is redshift 4, and you can see the dark halo is expanded to a core. and a similar thing is happening with the stars. So we think this is a natural way to form a ultra-diffuse galaxy, although it may not be unique. The stars expand with the dark matter. So putting this into a slightly different context, this is if you take a shell of dark matter and you add mass or you remove mass, then you can plot the ratio of these radii versus the total mass enclosed within Mi is the total mass within Ri, and Mf is the total mass within R final. If there's no change, then you're also along this line of 1, adiabatic contraction, Blumenthal et al. Is you're this line, and our simulations don't follow that, right? So the halo response is not adiabatic. One thing you notice that, again, I've color-coded these by the star formation efficiency, and there's a really nice trend. As you high efficiency, low efficiency, we can make this a little clearer by taking bins in star formation efficiency. And so this is 40%, 26, 16, 8, 3. And then I can compare this to the Gnedin contraction model. And basically, the Gnedin model is over-predicting the contraction. You just compare lines with similar colors. Gnedin model can predict expansion, but it's basically just very, very weak. Okay, so we want to understand this better with a new model. Okay, so here we can considering a shell of radius r and mass m. Adiabatic inflow, halos contract. Impulsive outflows, you get expansion. And what you see here is if this recovers the result that if a virialized system loses half its mass, it becomes unbound. Right, okay, so this expansion. And then what happens is you can now do a cycle of inflow and outflow with a ratio between the outflow and inflow as beta, and you get this equation. If you set, and of course, yeah, you can do this n cycles, and you just take the power of this. So what's interesting then, it's easy to show this in a plot. If you have one cycle, if you have equal inflow and outflow, not much happens until gas fraction or F increases, and then it blows up, right? So the outflows have a stronger effect than inflows when F is high. And what's interesting is when you have net inflow, so this is beta of less than 1, it's not so clear with one cycle, so I'll just show you with 10 cycles, 100 cycles. And so you can see that when you have a low outflow fraction, you get net contraction. But then there's a maximum contraction. And then when the outflow fraction is high, then you get expansion. Right? And so you can think of the outflow fraction is essentially, it's limited by the gas fraction in a halo, in a galaxy. And so at small radii, you have high local gas fractions. And at large radii, you have low local gas fractions. And so then we can use these equations. We can choose different values of the number of cycles, and we can find curves that provide a reasonable match to these. Right, this is not really a fit, but it's the thing I want you to get is that you can understand the trends, the shapes of these curves, just with a simple model of inflows and outflows. So have I run out of time? Okay, so I don't really need to say, well, I was going to say, this has already been shown before, the too big to fail problem. So you've seen this before, that the simulations, the halo expansion can match the stellar kinematics at the half-light radii. The other thing that is interesting is the velocity function problem. And so at a given velocity, either you've got too many objects or the velocities are too low. And so we looked at this with the Niehaus simulations. We created mock observations of H1 line widths with different orientations. And the red points are implied H1 velocity function. So we don't have an overabundance problem when we do mock observations. Okay, so I will finish there. So in summary, the halo response, at least in our simulations, is correlated with at least two parameters, the star formation efficiency and the compactness of the galaxy. And we can understand the radial dependence of the contraction expansion in terms of cycles of inflows and outflows. And there's a few other corollaries. I'll take any more questions now.
This time works. Aaron, so your adiabatic contraction and expansion is adiabatical processes, yes?
No, so the outflow is impulsive. The inflow is adiabatic, but the outflow is
But how you put energy in outflows? You need to put non-adiabatical process. Otherwise, it's reversible. So
Yes.
what's the source of entropy? What? No, it's the same as adiabatic contraction. You're going to go back and forth.
No, the point is
You need
that
to put
if
your
the,
energy in some form, right? Otherwise, it's
yeah,
a
it's from
trick of
supernovae.
approximation.
It's from supernovae.
No, it's not super. I mean,
Yeah.
no, the movie, it's a different story. This is simple spherical model. You do mass in, everything contracts. You mass out, everything expands.
Yeah, so
the
this
same
is-
mass
this
goes
is
in,
adiabatic
goes
expansion.
in the same state, unless you have problems with your approximations. If it's a adiabatical process, it's reversible.
Yes, but the point is it's not adiabatic. The outflows occurred on a much faster timescale than the dynamical time.
Much faster doesn't mean it's not adiabatic. The speed is not adiabatic and not adiabatic. It's irrelevant.
We should discuss this later.
Okay, one last question from you here.
I suppose it's not very difficult to look at the metallicity. I wonder whether you look at metallicity.
Metallicity. I've not looked at it. We've looked at the metals. Nihao reproduces the stellar metallicity, stellar mass relation. Yeah.
Okay, thanks very much, Aaron.